going to the waveforms for gravitational wave observation by Deborah Ferguson, who is one of our part of our scientific organizing committee. Deborah?
Yeah, all right. Just setting my timer real quick so that I can get you guys out promptly in time for lunch. Okay. All right. Wow, that's a big screen.
Isn't it great?
This is fantastic. All right. The laser points are working. That's all.
Right.
Fair. All right. Well, okay. Anyhow, that's a good point. I kind of forgot about the people online. That's fair. Okay. So hi, everyone. I'm Deborah Ferguson, as he just said, and today I'm going to give you guys a bit of an introduction in how we use numerical relativity simulation specifically, but kind of waveforms in general with LIGO, kind of as a motivation for one of the reasons why we do this. There's lots of ways in which just studying black holes is informative in and of itself, but one of the things that's nice is how we can use them to actually listen to what the universe is telling us that LIGO is able to see, especially since we get to go to LIGO on Wednesday, and so hopefully give a little bit of extra excitement to that. So this, yeah, definitely, if anyone can't hear me online, do let me know. I'm not sure which thing is the speaker and where I need to be shouting at.
I think you're supposed to. Anywhere is fine.
Oh, neat. Okay. All right. So this picture right here is one of the numerical relativity simulations that I ran for GW 1905-21, which some of you guys may have heard of, because it was the first direct detection of an intermediate mass black hole. It was the most massive black hole that LIGO has been able to observe. And here you can see a 2D projection of the gravitational waves as these two black holes merge. All right, so I think everybody in this room is already familiar with what black holes are, but just to make sure that we all have the same terminology, I'm going to be talking about Kerr black holes that have a mass and a spin. There's not that, well, there is some work being done with like charged black holes, but for the most part, LIGO isn't really involved with that. They're mostly just looking at masses and spins. All right, and when you have two black holes that merge together, each of which has their own mass and spin, they produce these gravitational waves, and you can see the 2D projection here, and then this line is the 1D projection line of sight that you would see of these gravitational waves. This is what LIGO would be able to observe, and what we want our numerical relativity simulations to produce, and produce template banks of, so that we can feed them into LIGO. All right, so as you change the mass and spin of your black holes, you change the shape of the gravitational waves that you produce. And as was mentioned earlier with the units and the way we're able to set up our simulations, we're able to set the total mass to be 1. And so rather than dealing with the mass of each black hole, we can introduce a new parameter for mass ratio. And so you can see how changing these parameters changes the shape. As you change the mass ratio, you can see how the frequency changes and the shape of the the gravitational waves change. And similarly with if you change the spin. I stop at 0.8 here because it's kind of hard to simulate black holes with higher spins than that. There's definitely tools that do it, but on this one, this I actually generated using a model, which I'll tell you about more in a minute. All right, so that was a quick introduction into black holes, which you'll hear way more about this week. But now I want to do a quick introduction into LIGO and the gravitational wave detectors. And I really like this visualization that came out of the LIGO lab that shows the basic idea for how this interferometer works. So the general idea being that you have a beam of light that gets split and reflected, comes back, and then you see this. But let's look at this more detailed. So the wave goes down, travels down each arm, reflects off of a mirror, comes back, and then is brought back together at the beam splitter and goes over here and is detected at the photodetector. And it's set up such that when there's no gravitational wave passing through, there's perfect destructive interference, and you should see no light in a perfect world. As the gravitational wave comes through, it stretches and compresses each arm, which changes the interference pattern, and then you see this light. And that's the strain that you're able to observe, which is that change in length divided by the length. And you're able to see that over here. Now, in reality, LIGO is a lot more complicated than this, but this is the overall basic idea of how this interferometer works. All right, so there are a number of gravitational wave detectors currently. There's LIGO Hanford and LIGO Livingston. We get to go see LIGO Livingston. There's Geo 600, Virgo, Cagra that joined somewhat recently, and then the proposed LIGO India that will hopefully join us someday soon. And to date, we've got, I think, 90 gravitational wave detections. Here you can see the color coding is based on the observing run, right? So we've got the first observing run up there in the purple, second observing run in the red, and then the purple is the third observing run. And you can see that it is becoming much more frequent. We are seeing a lot more gravitational waves than we ever did at the beginning, considering it's almost been a decade now. That's unnerving. But I was gonna say it's only been a few years since the first detection, but that's a little less true. The point still being, we've gone from having one and it being novel and just a proof of concept that we were able to detect something, to now we have a whole suite of gravitational wave observations, and it's a genuine way that we can observe and listen to the universe. What these plots are actually showing, such as this one here, I'm just people online, I'm pointing to one of the bright ones over here, is this is the time frequency, or well, this is, sorry, time frequency plot with amplitude being colored. And so you can see what you often hear of as the chirp, as it's increasing frequency for a particularly loud signal. And that's, you hear that whoop kind of chirp thing that I'm sure you've heard if you turn it into sound waves. All right. Maybe. Okay. Now, in addition to the fact that most of those have been binary black holes, there have also been observations of binary neutron stars and neutron star black holes. And that's something that Einstein Toolkit is really great at simulating, and not to say unique, but it is one of the big benefits of Einstein Toolkit is our ability to explore things like neutron stars. And so this is a simulation that one of the graduate students at UT Austin ran of a neutron star merging with a black hole, and then I did a visualization of it. This one is consistent with one of the neutron star black hole detections that LIGO had. Once again, you see the gravitational waves in 2D. Very jumpy. That's not the video. Just my own
that happens over Zoom.
Oh, is it just because it's Zoom?
Yes.
Well, for what it's worth, these videos are all on our YouTube channel, the Maya collaboration. So if you want to see them not jumpy, go there. Tell your friends. All right, so what these gravitational waves look like in the frequency domain and in the time domain, I think is useful to see. So we're all very used to seeing these signals over here, I think, which is that strain, you have the in spiral, and then you have a peak for merger, and then the exponentially decaying bring down. And this is for a couple of the events, and how much of the signal you're actually able to see in a detector with LIGO. And then we often talk about things like frequency band and sensitivity band. And I think if you're not particularly on the data analysis side or on the LIGO side, sometimes that information can get lost by what we actually mean here. And so I like to show this frequency plot over on the left so that you can kind of understand what this means. So this plot over on the left is the frequency versus essentially how sensitive the detector is. It shows the strain scaled interestingly, but it is this noise curve that you see that looks kind of like a bucket. That is the sensitivity of Livingston and Hanford. So qualitatively speaking, if the signal is above that noise curve, it can be seen, and if it's below that noise curve, it can't really be seen. And then each of these events is shown over there in the same color as to what that gravitational wave looks like in the frequency domain. And one thing that I think is particularly useful to note here is how your total mass of the black holes changes where you fall in the frequency domain. So if we look at the most massive system where you can see we only saw a couple cycles, well, the reason we only saw a couple cycles is because it merges earlier, it merges at a lower frequency earlier in the frequency band, so we don't see as much of it in spiral. Whereas this one, GW 15, 12, 26, merges at a much higher frequency because it's much lower mass, and so you're able to see a lot more of them in spiral. So that's what gravitational waves look like as you would see them by the detector. All right, now how these things actually get found by LIGO. Well, there are a number of different search and parameter estimation pipelines. So there are modeled searches that take a template bank of waveforms and then search for them by comparing them to the data, moving them across the data, and finding a match, finding where it looks like the data. This is really great for systems that we expect to see and are able to model well, such as binary black holes being one of the big things that we're able to model and we're able to create templates for. But same thing with neutron stars, black holes, and binary neutron stars. Some of those search pipelines, PyCBC, GST-LOL. Rift is less of a search pipeline, more of a parameter estimation pipeline, but still templated. Then there's unmodeled searches, which just look for coincident excess power. So they just look for a spike in the power that that photodiode sees, essentially, in the gravitational wave. And by coincident, I mean you see it here and you see it in Hanford, and so it's unlikely to have just been noise. What's great about that is that you can search for both unexpected signals or unmodeled sources, or for things that are just a burst. Good for if you're trying to look for supernovas or things that we don't even know to expect. CWB, OLIV, and phase wave are some of those searches / parameter estimation pipelines. All right, so this was the first ever detection, GW 150914, in Livingston on the right and Hanford on the left. And you can see the initial noisy data up top. And then the second panel shows it fitted with or overlaid with some gravitational wave templates. And we've got the numerical relativity is the solid line, red on the left, blue on the right. And then you've also got models, which I will explain more about in a minute, for both the burst type of looking or like the unmodeled way of looking, which is the wavelet approach, and the template. But point being, you get this data, you need to somehow make that look like a waveform in order to figure out what parameters led to it. And that's what's happening in this second panel. And then you can subtract that template from the data and you get a residual. And if that residual looks like noise, and then this is the time frequency plots for those. All right. I really like this visualization from Ryan McGee at Caltech on the modeled searches and how they work. So you can see a noisy data stream here. If you've got a good eye, you might be able to already spot the gravitational wave signal. No worries if not. But what you do is you take a waveform template and you slide it over the data and you compute a noise weighted inner product and you find where it spikes. And that's where you had a gravitational wave signal. And if it matches, if that's your template that matches your data best, then you have some idea of the parameters of the black hole that produced that template is likely the parameters of the black holes that produced the data that you observed. Okay. Also, we can use gravitational wave observations. So, well, okay. One of the big things that I mentioned is one of the big reasons that this is all exciting is that we're now able to see so many black holes that we're able to start doing accurate parameter estimation on them and actually understand the populations of black holes that we have out in our universe. So that's one of the big exciting things. But another exciting aspect is the fact that we can use these to start doing tests of GR and probe beyond GR theories and things like that. So I will mention these real quick, but I also just want to say that for more information on all of this, go see Tests of General Relativity with GWTP3. I've mostly just summarized some of their main tests of GR that they do in that paper. So go reference that paper. But one of the things I just mentioned on the previous slide was, or 2 slides ago, was residual tests. So subtract out the template that fit your data best and see if what's left is consistent with noise. If it doesn't look like it's consistent with noise, then either that template didn't fit very well, or if none of our templates fit very well, then maybe there's something beyond GR happening here that we're not capturing in our template. In-spiral merger ring down consistency tests, or IMR consistency tests. One of the things about the no-hair theorem is that we can connect the mass and spin and things of the initial black hole, which describe the in-spiral, and predict what the final black hole should look like. And that entirely describes how the gravitational waves of the ring down should look like. But also you can directly measure the ring down and its decay rate and its frequency and find out the final mass and spin of the black hole. So if those don't agree, if you fit just the in-spiral and you fit just the ring down and you get inconsistent results, then that could also be a sign that maybe something beyond GR is going down. And you'll notice I've highlighted a couple things here in that kind of purplish color to point out why we need template waveforms for these tasks, why we need numerical relativity for these tasks, and why they're so important. And then there's additional parameterized tests that we do, or they do. I'm not going to go into the details of that, mostly because, well, I'm not an expert in that. All right. Okay, so just a reminder of what I'm talking about here when I say generating template banks and generating waveforms. For each mass and spin that you have of your initial black holes, you're going to get a different gravitational wave. And have this like 9, 8, 7, depending on how you define your parameters, dimensional parameter space. In this case, I say 9-dimensional parameter space. You've also got the eccentricity, which defines whether your black holes are orbiting in a circular way or quasi-circular, as we refer to them, because they're also decaying, or eccentric, so getting closer and further apart. All of those things change your waveform. So in an ideal world, we would have a 1-to-1 correlation here that we were able to just solve and model and know the exact, these are the masses, these are spins, this is exactly what the gravitational waves would look like. But that's what we want to have, is a template bank of these gravitational waveforms. But how do we actually do this in practice? How do we actually produce those waveforms? Well, we want to solve Einstein's equations, right? That's what we're all here to do with the Einstein toolkit, is solve Einstein's equations. They're very complicated equations, set of nonlinear coupled partial differential equations. And for the two-body problem, there is no analytic solution. So we have to come up with other ways of solving. And what other ways you use is dependent upon what type of system you have. And this diagram here, which you can go find in the LISA Consortium Waveform Working Group white paper, which is a hell of a mouthful, but has finally been published and released. And so would definitely recommend going and looking at that. Based on the fact that it's the waveform white paper, you can tell that it's going to have a lot of the stuff that I'm talking about today. Waveforms with gravitational waves. Okay, anyway, this figure is from that. But what is this figure actually showing? So we have 2 axes. We have the mass ratio on the x-axis. The numbers can be a little confusing because you can define mass ratio as either greater than 1 or less than 1, depending on which way you want to do it. But 1 is equal mass. As you move away from 1, it's non-equal mass. So on the left there, we're saying black holes that are comparably sized, and on the right, it's black holes that are very different size. And then compactness, in this case, is essentially how close together your black holes are. So in cases where our black holes are really far apart, so that blue region up there, you do weak field expansions, post-Newtonian, post-Minkowskian, and that is where your black holes are moving at much less. Wait, hang on. My next slide goes into this in detail. I just remembered. Yep. It's a problem with not practicing. Okay. So when your black holes are really far apart, you have orbital velocities that are really small compared to the speed of light. And this is really great for modeling in spiral. Black holes, again, are really far apart. There's the section in the waveform white paper to go back. 4.2. All right, now in case, why that works is, yeah, you're able to make approximations that work when your speed is much less than the speed of light. And so you can solve them analytically and semi-analytically and run efficient simulations. Okay, now when you move to this right region and you have one black hole that's a lot larger than the other, then you can treat the secondary mass as a perturbation to the background metric of the primary object. This lets you make simplifications that make it easier to simulate analytically or semi-analytically. It has also made huge strides in recent years, pushing towards equal mass ratios, specifically right now for non-spinning systems, but they've basically pushed down to equal mass in spiral, not quite merger, but it's making huge progress. They're starting to close that gap between the yellow and the red. Sorry, Zoom people, I keep pointing at things and forgetting. This is pushing lower and lower, which is exciting. Because there's these regions in the middle you can see that aren't well covered. Any way we can cover them would be great. All right, check out section 4.3 to read more about that. Then there are effective one-body models, for example, which are semi-analytic waveform models that approximate the whole system by mapping the two-body problem onto a effective test mass that moves in a deformed space-time. And that has, it kind of lets you cover the whole parameter space, and it's trained on small mass ratio and post-Newtonian and numerical relativity data. It's not going to be as accurate per se as any of these, but it gives you the benefit of being very fast and covering the entire parameter space somewhat continuously. So those are also great, and they have started making progress towards including eccentric and precessing spins. That might be the first time I've said precessing spins. So for those of you unfamiliar, when we say aligned or anti-aligned, that means your spin axis is aligned or anti-aligned with the orbital angular momentum. Precessing means not aligned with those, and you're going to get an orbital plane that precesses. Generally makes things more complicated, especially for models. Okay, then there are also phenomenological models, which use a physics-informed ansatz that they then train on numerical relativity data, post-Newtonian data, and fit the free parameters that they have. These are really fast to generate, which makes them ideal for searches and parameter estimation, because you can quickly see the initial parameters that led to the gravitational waves that you have. IMR phenom X, for example, is one of the recent more cutting edge ones. XPHM is really what I should have put there, which has precession and higher order modes, be the more accurate one there. Okay. There are both time domain and frequency domain models that just, train on either frequency domain or time domain gravitational waves. And they do this piecewise construction where you do in spiral, merger, and ring down somewhat separately, and then stitch them together. And this is also from that waveform white paper, so go check it out for more detail. Then there are in our surrogate models, which can be more accurate, but a little more limited. These interpolate between numerical relativity simulations. So should I answer questions as I go if someone reads them to me on the chat?
Yeah, that'd be fine. Why don't I?
Just someone keeps sending like private messages.
It looks like. I don't see them on my chat.
Whose chat is he?
Oh.
Okay. Okay. Well, if anyone sees one that actually is relevant and for me, let me know. Right. Okay. Numerical relativity simulations. We set the parameters of our black holes and we run a simulation that can take weeks, days, months, depending on the simulation. It's a big reason for checkpointing. But they're discrete. We have a point and parameter space. In our surrogate models, interpolate between them to create a continuous space. They're very accurate. This visualization I found on Vijay Varma's website shows this really well, that I really like. So here's a gravitational wave at one mass ratio, gravitational wave with a different mass ratio. And then you can keep making waveforms. There's the amplitude evolution. There's the amplitude evolutions again. Now you like find specific points on it, and then you can interpolate between them by doing a fit that connects all of them together. And now you can see, hey, at this other random mass ratio I didn't simulate, now I know what the amplitude evolution would look like. And this is very accurate when you're close to one of the training points for sure. If you're right on a training point, it should give you that exact value, so it should be very accurate. It's limited to the same coverage as numerical relativity waveforms have, also in terms of length, though there are some hybrid surrogate models that use both NR and post-Newtonian hybridized in order to create longer spirals. Okay, so I've talked a lot about all the different ways that we can simulate waveforms or produce waveforms, but we're all here for numerical relativity, so where is it still needed? Where is numerical relativity important? So I'll go through my list on the left, but I also want to tell you about this plot on the right. So this plot on the right is a sample of 4 of the public catalogs. There are some more, but these are kind of the most populous public catalogs. And so you've got the SXS in blue, RIT, Maya, and BAM, which are Einstein toolkit based. And this shows the coverage of that. So each point on the plot is a simulation, and we're showing the mass ratio, the spin, the aligned component of the spin, the precessing components of the spin, which is that perpendicular for both the primary black hole, which is A1, the larger black hole, and A2, which is the secondary black hole. And the diagonal just shows you the one-dimensional distributions, and the off diagonals are showing you 2-dimensional distribution. Some of the key things that you'll note where we don't have as much coverage is at high mass ratio, like anything above 4, it drops off pretty significantly. Just even that high mass ratio, but does make things much less efficient and challenging. So there's definitely parts of the parameter space that we really need to work on tackling. Okay, now what regions of that parameter space is numerical relativity particularly important for? Well, if you remember, based on this one I was showing you here, we need it whenever we have comparable masked systems that are close to merger or at merger. And so that's one of the main use cases, is comparable mass systems near merger. And then there's also the complication of eccentric and precessing systems. So a lot of the models are trained on NR. And so in order to have the models at all, we need the NR data. And so eccentricity and precessing is one of the big things where we still don't have enough NR data for models to take over that. Then there's matter. In any way, shape, or form, essentially, once you want to start adding in neutron stars or massive fields, or simulate what happens if you're inside dark matter or inside a cloud or you have accretion disk, well, we need to run full simulations for that in order to understand what's happening. Probing beyond GR theories, we still need to simulate those. Some of those can definitely be done with the semi-analytic approaches, but not all of them. And then, as I said, these are used to construct the model. So we need it covering the full space in order for models to be trained on them. But we also use them directly with data analysis. Rift, for example, can directly use numerical relativity to perform parameter estimation. And so to produce those waveform templates that we want to use to be able to listen to gravitational waves from LIGO, we need numerical relativity simulations, and we need us to run them. Now, there's still some challenges. We're going to need higher resolution simulations to make more accurate waveforms. This plot on the right is from a paper of mine from a couple years ago, where I show for current finite differencing cactus codes, or I guess any finite differencing code really, but right now this is our fourth order convergent code. As you increase the signal to noise ratio of your detection, so as your detections get louder and louder, and you want to make sure you're getting as much physics out of them as possible, what grid resolution do you need your finest grid to have? And so that increases as you increase the loudness of the signal, and any, systematic errors start becoming louder and more important than the statistical errors of the detection. So you need higher and higher resolution. When this plot was made, that horizontal line was the Maya catalog's highest resolution simulation. That's not quite true anymore, but it gives you kind of an idea still of like what's easy versus what's not. Below that line, kind of easy. Above that line, not easy. And so the blue line here was equal mass ratio, and even up to signal to noise ratios in the thousands, we're still doing fine. But as you start adding in higher mass ratio, so the red lines are Q6, or add inclination, so not observing the gravitational waves from directly above the orbital plane. I haven't talked about higher modes basically at all, but you start seeing higher modes, and those require higher resolution to fully resolve. And so it gets harder to resolve those as well. So challenges, we need higher resolutions, which means that we need more scalable codes that can become more accurate with less resources. And you're going to hear a lot about things like Carpet X. That's one of the big things that is pushing. So this is well on its way, but it is a challenge that we need to work on. Similarly, longer waveforms. We can hybridize with post-Newtonian, but that introduces some errors, and post-Newtonian is not going to be accurate all the way till merger. And so finding that balance of making numerical relativity waveforms longer to find the right place to hybridize, well, we need longer waveforms. And then, as you saw in that previous plot, there's still parts of the parameter space we need to cover more. We need higher mass ratios. We need more coverage of eccentricity. That plot I showed you, this one is only for quasi-circular simulations. When you do this for eccentric simulations, it is exceedingly sparse. It's happening. People are working on it. The Maya catalog, the SXS catalog, people are introducing eccentric waveforms, but it's sparse. The RIT is as well. Leave them out. All right. But eccentricity is one of the big areas we need to add more simulation. And then pushing higher spins, especially with precession. All right, and for all of this, we need to start thinking about next generation gravitational wave detectors as well. So I've been speaking mostly about the current age, but LISA, for example, has been officially approved, and so we know it's going to fly in the early to mid 2030s, and that might seem far away, but there's a lot of work to be done, and when you're thinking about covering an entire parameter space that's 9-dimensional, that takes time, and so we need to start working on these. Okay, so that's LISA. We also have that's the space-based gravitational wave detector. We're also going to have Einstein Telescope and Cosmic Explorer, which are our next generation ground-based detectors. And this plot, which I really like, shows for a given total mass and a given distance that we are from the source, how loud it'll be. The contours are the signal to noise ratio. And what you can see, well, that's for different masses, but for both Einstein Telescope and for LISA, we could reach signal to noise ratios in the thousands for some events. For reference, I think this is still true. LIGO's loudest signal that's in their catalog is like 32 signal to noise ratio. This is potentially going to be thousands. And so that's going to produce those challenges, like I said earlier, about needing more resolution is going to become really important as we prepare for next generation. All right, I'm just really excited about LISA. So some comments about this one too. I like this visualization that shows how LISA works. So that's our sun, the blue is us, and then LISA will cartwheel along following Earth. And so with those really long arms that you can tell from that versus LIGO, this is really long arms, that means that it will be at a much lower frequency, which means it'll see much more massive black holes, which actually this plot here shows you that. Lisa is most
10
sensitive.
minutes.
Lisa is most sensitive for black holes around 10⁶ solar masses, whereas ground-based ones are more sensitive in the 100 or lower total solar masses. Okay, right. Officially adopted, will fly in around 2034. Fingers crossed. Oh, shoot. Sorry. This I may have copied from a job talk that I gave a couple weeks ago. So here I'm bragging that I am chair of the Lisa Early Career Scientists. Whoops. But it will have unprecedented sensitivity for supermassive black holes, which is really exciting, and pretty decent localization as well, because as it cartwheels, it is able to localize in the sky with just Lisa able to see where the sources are coming from. And with the stationary ground-based detectors, we need multiple detectors to be able to pinpoint the locations in the sky. All right, so for my last slide, I think I'm going to let you guys out a little early for lunch, unless there's just lots of discussion. This, I think, shows a nice spectrum of gravitational waves. One thing that I will say is extremely confusing when I first saw it is that this bar going across, that's the frequency, is flipped from the way you would think about it. High frequency is on the left, low frequency is on the right. The reason it did that is because it shows increasing time scales. And so with LIGO, with the high frequency signals, we just see a signal for like a millisecond to possibly a few seconds. I think maybe one of the binary neutron stars was like a minute, but that's the order that you can see. Whereas signals that we see in LISA, the supermassive black holes that are merging at low frequencies, we'll be seeing signals in there that are spiraling for minutes, hours, possibly even years that we could see. And then if you move even further to lower frequencies, something I didn't talk about at all, but you've got like pulsar timing arrays, which are able to see even more massive black holes. And there's been some really interesting results coming out of that. Would definitely recommend going into some of the recent nanograph stuff. But yeah, what's so exciting with us having ground-based detectors and space-based detectors and pulsar timing arrays as well, is that we're able to cover the whole frequency range of gravitational waves. And we need template waveforms that allow us to study all of these. We don't want numerical relativity or waveform development to be what limits us from using all of these exciting detectors and being able to observe the universe in all of these ways. We want to make sure that we are on the cutting edge of that as well. So just to wrap up here, gravitational wave detectors, we've observed at least 90. That's as of the third observing run. The fourth observing run is ongoing. And so there's going to be way more of that as well. Some of those things give public alerts. And so you can't see all the component masses and things like that, but you can see the detections that have happened. And we're on order of multiple per week at this point. But searching for those detections and characterizing them requires having template waveforms that predict what those gravitational waves should look like. And there's a number of different techniques to do so. And for comparable mass systems, particularly near merger, that's where numerical relativity is particularly crucial. And as we're preparing for next generation detectors, there's still a lot of challenges facing NR, and we need to make sure that that we're ready to face those challenges, and that's what the people in this room are for. All right, thank you. Yes. Sure.
What happens at a certain point, we just not move the data whatsoever?
Oh, my early ones, like.
You have to repeat the question.
Oh, hang on. Do you mean real quick? Do you mean here? Are you talking about in the center? Okay, so he's asking why I've essentially excised the data here in the middle, and you don't see what's actually happening right near the black holes. So the thing is, when we talk about gravitational waves, they're really defined as a perturbation on the metric in the weak field regime. And so for the most part, gravitational waves really are well-defined way out here. And right near the black holes, It looks kind of wonky, and it'll like shoot up to infinity. Because this is something that decays, it's like 1/r. Near the black holes, if I didn't cut that out, you would just see a spike that goes to infinity. But that's not actually informative. It doesn't actually mean anything really. And so it is a lot less confusing to just cut it out and not bother showing it. When what's important is the further out behavior anyway.
Quick talk,
Thank you.
when we're talking about the NR calculator with stuff, so when they take the NR data bank calculator, presumably the NR data bank.
Sure.
That or
Yeah, so there are a number of different models. There are a lot of models that are specifically trained, for example, on just aligned spins, or some maybe even that are just trained on non-spinning. They usually have a range of validity for things like the mass ratio, where they might say this is only applicable up to mass ratio 4. Some of them will say you can push it up to mass ratio 7 or 8, but the accuracy will be lower because, yeah, it's going to be more accurate where there's more training data. So that's also a reason processing models are often less accurate because there's a lot less training points there. But usually the models do a good job training on a subset of the data and then testing on other data points and giving you a decent sense of what types of mismatch errors you might expect. And usually the papers will describe that relatively well, so you can get some sense of what the errors are going to be. But yeah, if you're near where there's a lot of training data, equal mass or close to equal mass aligned spins, the models at this point are pretty dang good. But as you start adding in precession, precession's getting pretty good. But as you start adding in eccentricity and things like that, the models are going to be less and less accurate right now. Oh, what software did I use for my visualization? Python. I built essentially my own kind of visualization tool on top. I don't know why I just stopped on an arbitrary page. I was trying to go back to the visualization and gave up. Anywho, I built a kind of library, well, not a library, just my own tool on top of a Python library called MayaV, which is funny to anybody who knows, like, the code I work on is called Maya, and I wrote an analysis library called Maya Waves. But MayaV visualization is actually entirely unrelated and is something someone else entirely wrote that I just like. So that's the underlying Python library that I use, and then I've written some software on top of it to take Einstein Toolkit data and generate visualizations out of it. Yeah.
What about constant charge back? How would
Yeah. So if you, oh, thanks. Sorry. I think I did 2 for 3 on doing that successfully. She asked about visualizing and simulating binary neutron stars, and charged black holes. So for binary neutron stars, we definitely have simulations of that. Anytime you have neutron stars or matter involved, you come into questions like equations of state and things like that add more decisions you have to make in terms of your simulation, more parameters to describe them, things like that. But we do run them. We do run neutron star simulations. I didn't include any in this talk, but if I may brag, I do have a pretty cool neutron star visualization on our YouTube channel if you look up Maya collaboration. So we can definitely visualize those. I've never done anything with charged black holes. There's definitely, I know. Yeah, I can't really answer anything about that, but I think some people do.
right? And so to talk of that, if you were to use, there was a slide about parameter. If you were to do parameter estimation on LIGO data by using your simulation, would you be running on
Sure. So the main, oh yeah, if you're to use numerical relativity simulations directly for data analysis with like LIGO data, what are the techniques people use for that? Is it something that you can implement? There are definitely, so one of them that I mentioned was Rift. That was something that came out of RIT, but one of the postdocs who works on that, Jake Lang, is at UT Austin, which is where I was before now. And so I've worked with him on using Rift to take LIGO data and directly do parameter estimation with numerical relativity waveform. And so that one, I think, is using Monte Carlo methods to do this. It's one of those things where using waveform models is easier for parameter estimation for a couple reasons. One of which being you pretty much have if you have an analytic or semi-analytic model, then you can say specifically the parameters you want, and within between milliseconds to minutes, depending on the model, have waveforms out. Whereas with numerical relativity, you need months or at least days. So for those, you could set up a grid of exactly where you want your points in the parameter space, and that can make parameter estimation easier. You can also do a coarse parameter estimation and then make a more refined grid as you hone in on it. And with numerical relativity simulations right now, at least, you have a very unstructured grid. So I know it makes it more complicated. I don't personally actually do parameter estimation, so I can't talk about any of how the Monte Carlo or the Bayesian methods are actually doing it, but I know that there are tools that can do it, like Rift, that'll do it directly on numerical relativity waveforms.
So now that we have this many detections, how much of a challenge was it to just keep up with everything? I suspect that the more these are to look at these visually, what's the progress of getting active automated pipelines to go beginning to end maybe and our simulation?
Yeah, so he was asking about as we're getting more and more detections and it's becoming less scalable for humans to actually go through and analyze each detection manually and keep up with that. What's the process that's happening to make these things more automated and things like that? Yeah, that's definitely a challenge that I think the LIGO collaboration is going through right now. Over the last few years, there's definitely been a lot more automation that has happened with these pipelines. So for example, as soon as the detector automatically sees like a spike for the unmodeled ones, for example, sees a coincident spike in power, then it can send out alerts already to like astronomers who are like, hey, look at this. And so there's things that are already automated and do things quickly. And so a lot of the low latency pipelines are well automated and fast at this point. The full pipelines of doing all the extended, more thorough parameter estimation, I think some of that still has a more manual aspect, and you have people whose entire focus is on doing things like parameter estimation for these things. But I think it's an ongoing progress. Things like requesting in our follow-ups is definitely something that needs to be improved. I feel like there's still often too little collaboration between the different working groups within LIGO for some of these things. And so the waveform group sometimes is too disconnected from the parameter estimation group and things like that. And so some of that isn't as automated. But I do think oftentimes whenever there is an interesting event, everyone becomes very aware of that. And that's the type of things that are more useful for in our follow-ups. We used to be running in our follow-up simulations for every event, pretty much take the highest likelihood parameters and run an NR simulation. But when it's just like, oh, it's mass ratio 1.2, line spins of 0.3, I think people got a little less interested in running follow-up simulations, but we still run targeted ones when it's like, this is looking pretty high mass ratio 8, or things like that. There's still a lot of interest, but I would love to have a pipeline that does all of it on the LIGO side, but even if connect it through and have my thing automatically create a parameter file and run it or something for interesting simulations would be a lot of fun. But I think it's an ongoing growing pains type of thing.
Couldn't you just have like a public thing, like here's a signal that we got, and then other groups could on their own just grab it and try to run numerical simulation?
I think
Or
there's,
is that not a, or is
there's-
that too politically
there's a
unfavorable?
lot of he was asking about like, can you just essentially make the data public and let other groups start searching for signals? I think that there's a lot of politics involved with that. Anytime you have NSF funded things, you're going to end up with a lot of politics, and especially things where one of the tricky things with LIGO is that there's a lot of, I mean, we kind of talked about this earlier in your talk as well. Some of the thankless work that happens with things like code dev, and yet people still need papers and things like that. And so with a LIGO collaboration, there's a lot of thankless work. And so by being a collaboration member and promising a certain amount of your time, you also get guaranteed to be on certain papers and get access to the data first. And so there's some things like that make being in the collaboration worthwhile. Then there's also the fact that a lot of the data analysis is exceedingly complicated in order to denoise, because that beautiful little animation of how the LIGO works is not at all accurate in terms of all the stuff that you have to do to get rid of Earth's noise through that data. And when you release the full data, you get a lot of well-intentioned but less knowledgeable people analyzing the data and making claims that are less and less accurate. And so that's also one of the challenges. The big thing that they do right now is essentially do an alert that doesn't really include the data, but includes things like the sky location so that people can do follow-ups. And then once you publish a catalog, they usually release the data, maybe not the full data stream, but the data around each event. I know a lot of people wish that there would be a longer data chunk around each event, but I think that's kind of semantics that starts to sort out. Did I see a chat question? I thought my periphery saw something pop up.
Yes, how can we model GWs from modified gravity theories, especially when we have limited computational power? At least to do the modeling analytically first and move to the numerical model.
I don't need to read it because you just, okay. I was about to repeat it back.
No.
That is definitely ongoing work. You're going to hear some talks later this week. My current boss, actually, Helvi Vitek, I think, is giving a talk on Beyond GR. And so you'll hear much more detail on that. So I'll defer to future talks. But yeah, there's lots of different Beyond GR theories. There's lots of different methods for exploring them. There's people exploring them in post-Newtonian. There's people exploring them in numerical relativity. Adding in those extra terms definitely can complicate the whole way that we split Einstein's equations into this lovely 3+1 that we're able to evolve. And so it's not as easy to implement a new theory of gravity as it is to just change the masses of your black hole. You know, it takes a lot of development work, but it's an ongoing thing that people have been making a lot of progress in over the last couple of years.
When LIGO says detected gravitational-wave, that is math, these are essentially labels that come out post function. You want to trouble that these labels match the are more specific than more trace for now. I guess the left one.
Yeah, well, so I mean, for like things like mass and spin and whatnot, since most of the models are calibrated to NR, that generally matches the way that we define things in R. Once you're starting to do orbital parameters like eccentricity, so he's asking about like when detections come out of LIGO and they'll assign parameters like this detection has this eccentricity. That eccentricity may be ill-defined depending on the type of waveform modeling you're using. So post-Newtonian uses a certain definition. Numerical relativity, every code uses a different definition. And so, you know, how does all of that work? And is this getting more and more problematic? And yes, it's getting more and more problematic because, so one of the things about eccentricity is that it's the first, or one of the first things to radiate away. And so usually by the time you reach merger of black holes, they've circularized and don't have much residual eccentricity. And this is why, for the most part, people haven't been too worried about it, and it wasn't one of our priorities for LIGO. But there has already been some evidence that we may have seen eccentric events. But also, as we start thinking about next generation detectors that will see more in spiral, we expect to actually observe eccentricity, and we need to be prepared for it. The problem is it's a Newtonian concept in terms of the actual mathematics. And with post-Newtonian, you can kind of still define it in some sort of cohesive way. But once you're in full GR and you're in the merger regime, there's no one way to define how eccentric an orbit is. And so you can kind of qualitatively be like, ah, yes, this was eccentric. But to be like, ah, this was eccentricity 0.3 will mean something very different to different groups and different people. And so this has been a huge push over the last few years, is to find and it can also be gauge dependent, depending on whether you're computing it from the orbits or the gravitational waves. So there's been a huge push over the last few years to come up with an eccentricity definition that you can compute directly from the gravitational waves. And then you don't care about what value people are using when they input into their code per se. You more care about, once you have the gravitational wave out, here's what the eccentricity is, and that should be the same whether you're a model in our simulation or whatnot. And so that's been relatively successful. I think people are kind of converging on a few definitions, but it's definitely not solved. All right. Okay, well, if there's nothing else, let's get to lunch.
Right, lunch should be sitting out for us in, well, might be there already, but it might be 4 minutes from now.
Oh, no.